Hi, this is the Quasarea channel, and today we will embark on an incredible journey to the border between the quantum world and the infinity of space. Get ready to see the universe from a completely different perspective, where reality turns out to be much stranger than any fantasy. Imagine that you are standing under a night sky strewn with billions of stars. Every photon of light that reaches your eyes from distant galaxies has traveled an incredible path through the cosmic void. But what if I told you that this photon behaved completely differently from what you think? That it was both a wave and a particle, that it could have been in several places at the same time until you looked at it? Welcome to the quantum cosmos, where the laws that govern the smallest particles of matter create the most grandiose phenomena in the universe. Let's start with the most mysterious phenomenon that even Einstein called creepy long-range action: quantum entanglement. Somewhere in the depths of space, in a nebula, two particles of light are born from the same quantum event. Maybe it happens in a supernova explosion or in an accretion disk around a black hole. These two particles become quantumly entangled, connected by an invisible filament that doesn't break even when separated by light years of space. Now imagine that one of these particles is flying towards Earth, and the other is hurtling in the opposite direction, towards a distant star 1,000 light years away. When the first particle enters your telescope and you measure its properties, such as the direction of rotation or polarization, its entangled sister instantly knows about it and takes the opposite state. Instantly, not at the speed of light, but instantaneously, regardless of distance. This is not science fiction. This is the reality of our quantum cosmos, confirmed by thousands of experiments. Satellites are now flying in space that use entangled photons to create completely secure communication channels. China's MOSI satellite is already demonstrating quantum teleportation over distances of more than 1,000 kilometers between orbit and ground stations. But what is quantum teleportation really? This is not what is shown in Star Trek, where Captain Kirk dissolves in one place and materializes in another. Quantum teleportation is the transfer of the quantum state of a particle, its information, and not the matter itself. However, in a space context, it opens up mind-blowing possibilities. Imagine a spacecraft flying towards Alpha Centauri for light years from Earth. Traditional radio communication would take 8 years to exchange messages back and forth. But if there are entangled particles on Earth and on the ship, we can use them to instantly transmit information about quantum states. True, there is a subtlety here. For full teleportation, you still need a classical communication channel that works at the speed of light, but the quantum information itself is transmitted instantly. Let's dive deeper into the mechanics of this phenomenon. Every elementary particle in the universe exists in a state of quantum superposition until the moment of measurement. An electron rotates clockwise and counterclockwise at the same time. A photon passes through two slits at the same time, and a quark is in several energy states at once. It's not our inability to measure accurately. It's a fundamental property of reality. In space, this quantum uncertainty takes on grandiose proportions. Take, for example, the cosmic microwave background, the afterglow of the Big Bang that permeates the entire universe. This ancient radiation encodes quantum fluctuations that occurred in the first fractions of a second of the cosmos' existence. These tiny quantum oscillations, subject to Heisenberg's uncertainty principle, stretched to cosmic proportions during the period of inflation and became the seeds for the formation of galaxies, stars, and ultimately you and me. Can you imagine? Quantum effects occurring on scales smaller than the atomic nucleus have determined the structure of galaxy clusters millions of light years across. The microcosm created the macrocosm. Now let's talk about black holes. These cosmic monsters, where quantum physics meets general relativity in a dramatic confrontation. When a massive star collapses into a black hole, according to classical physics, all information about the matter that has fallen beyond the event horizon is lost forever. But quantum mechanics says that information can't be destroyed. That's a fundamental law. This paradox has tormented physicists for decades. Stephen Hawking showed that black holes are not completely black. Quantum effects at the event horizon cause black holes to emit radiation, Hawking radiation. Pairs of virtual particles that are constantly being born and annihilating in empty space due to quantum fluctuations in the vacuum can separate at the event horizon. One particle falls into the black hole and the other flies away, carrying away the energy. Slowly, incredibly slowly, the black hole evaporates. But here's what's really striking. The information about what fell into a black hole can be encoded in that radiation through quantum entanglement. Each photon of Hawking radiation is entangled with its partner falling below the horizon and with previously emitted photons. This creates an incredibly complex web of quantum information stretched across space and time. Imagine a cosmic web of quantum entanglement connecting all corners of the universe. Particles born together billions of years ago in the nuclear furnaces of the first stars may now be at opposite ends of the observable universe, but are still connected by quantum correlation. It's like the invisible nervous system of the cosmos, where measurement at one point instantly affects correlations at another. Astronomers are already detecting quantum effects on a cosmic scale. When light from distant quasars passes by massive galaxy clusters, it is bent by gravitational lenses. But this light is also subject to quantum effects. Individual photons can take different paths around the lens and interfere with each other, creating quantum interference patterns at cosmological distances. There are even more surprising phenomena. In neutron stars, where matter is compressed to incredible densities, electrons and protons merge into neutrons to form a state of matter that is essentially a single giant atomic nucleus the size of a city. Inside a neutron star, there may be quark superfluids and superconducting states of matter, governed by quantum mechanics, but manifesting on scales visible from space. Magnetars, the most magnetized objects in the universe, have magnetic fields so powerful that they warp the very vacuum of space, altering the quantum properties of empty space. In such fields, it becomes possible to spontaneously generate particle-antiparticle pairs from a vacuum, turning empty space into a seething cauldron of quantum activity. Let's now talk about the most mysterious experiment that humanity has ever conducted in space. We are talking about checking Bell inequalities using light from distant quasars. To understand its significance, we need to return to the fundamental question: is quantum entanglement really real, or are there some hidden variables that we simply can't measure? Scientists have used light from quasars billions of light years away to randomly select measurement parameters in experiments with entangled photons. The idea is ingenious. If hidden variables exist, they must have been laid down before light left these quasars billions of years ago. The results confirmed quantum mechanics. Reality is really non-local. Particles are really instantaneously connected through space. This has profound philosophical implications for our understanding of the cosmos. The universe is fundamentally interconnected in ways that challenge our intuition about space and time. The distinction between here and there is in some ways illusory at the quantum level. Now, let's consider the practical applications of quantum phenomena in space research of the future. Quantum computers on board spacecraft will be able to instantly solve the most complex navigation problems, simulate quantum processes in exotic space environments, and crack the fundamental secrets of physics in real time. Quantum sensors of incredible sensitivity will make it possible to detect gravitational waves with unprecedented precision, pick up the faintest signals from distant civilizations, and even possibly detect dark matter particles, those elusive ghosts that make up most of the mass of the universe. Speaking of dark matter, quantum physics may hold the key to solving this cosmic mystery. There are theories that dark matter is made up of exotic quantum particles, such as axions or WIMPs, that interact almost never with ordinary matter, but exhibit quantum properties. Detectors deep underground and in space hunt for these ghostly particles, trying to catch the rarest quantum interactions that could betray their presence. Even more mysterious is dark energy, the mysterious force that accelerates the expansion of the universe. Some physicists suggest that it is related to the energy of the quantum vacuum. Remember, I mentioned virtual particles that are born and disappear in empty space? The energy of these quantum fluctuations can fill every cubic centimeter of space, creating a negative pressure that pushes galaxies away from each other faster and faster. However, there's a huge problem here. When physicists try to calculate the energy of the quantum vacuum theoretically, they get a number that is 10 times greater than the observed dark energy. This is perhaps the worst prediction in the history of science, and it shows how far we still are from understanding how quantum mechanics works on cosmological scales. Returning to quantum teleportation, let's imagine more ambitious applications. What if we created a network of quantumly entangled particles distributed throughout the solar system? It would be a space-based quantum internet, allowing for the instant exchange of quantum information between Earth, Martian colonies, stations on Jupiter's moons, and research probes in the Kuiper Belt. Such a network would open up opportunities for distributed quantum computing on a cosmic scale. Imagine a quantum computer whose processing elements are spaced apart by astronomical distances, but work as a single unit due to quantum entanglement. The computing power of such a system would be unimaginable. But there is an even more fantastic prospect. Some theoretical physicists have suggested that the very structure of space-time may arise from quantum entanglement. In this picture of the universe, the space between objects exists because the particles that make up those objects are entangled in a certain way. By changing the patterns of entanglement, it may be possible to change the geometry of space-time itself. Sounds like magic? This is the cutting edge of quantum gravity, a field where physicists are trying to unify quantum mechanics with Einstein's general theory of relativity. If these ideas are correct, manipulating quantum entanglement on a cosmic scale could make it possible to create wormholes, warp space for faster-than-light travel, or even construct new regions of space-time. Of course, we are still very far from such technologies. But the very fact that we can seriously discuss these possibilities shows how deep the connection between quantum physics and the cosmos is. Let's go back to the origins, to the first moments of the universe. At the moment of the Big Bang, the entire cosmos was compressed into a quantum fluctuation smaller than an atomic nucleus. In this primordial state, there was no difference between quantum mechanics and cosmology, between the microcosm and the macrocosm. The entire universe was a quantum object. Within the first fractions of a second, cosmic inflation occurred, an incredibly rapid expansion of space. Quantum fluctuations in the vacuum were stretched to cosmic scales, becoming the seeds of the structure of the universe. Every galaxy, every star, ultimately, every atom in your body comes from these quantum vibrations of the primordial cosmos. There's an amazing idea in cosmology. Our entire universe could be a quantum fluctuation in a kind of meta-vacuum, a random bubble of space-time that arose out of nothing. Moreover, if this is the case, then there must be infinite other universes, other bubbles, each with its own laws of physics, arising from the quantum foam of the multiverse. In some of these universes, quantum mechanics may work differently or not exist at all. In others, the fundamental constants of nature are different, making it impossible for stars, atoms, or life to exist. We live in a universe where quantum laws are just right for the emergence of complex structures and a consciousness capable of thinking about these laws. This brings us to one of the deepest mysteries of the quantum cosmos, the problem of measurement and the role of the observer. In classical physics, the universe exists in a certain state, regardless of whether someone is observing it or not. But quantum mechanics tells us something completely different. A particle exists in all possible states at the same time until a measurement occurs, and only then does the wave function collapse into one particular state. This begs a mind-boggling question: what happened to the quantum state of the universe before the appearance of observers? Billions of years of cosmic history passed before the first conscious being capable of making a measurement appeared. Has the universe been in a state of superposition all this time? And what is considered an observer in general? Is consciousness necessary? Or is any physical interaction enough? One interpretation, the many worlds interpretation of quantum mechanics, offers a radical solution. It states that the wave function never collapses. Instead, with each quantum event, the universe splits into many parallel realities, one for each possible outcome. When an astronomer measures the spin of an electron coming from a distant star, the universe splits into two. In one, the electron has a spin up, in the other, it has a spin down. Both versions of the astronomer continue to exist in parallel branches of reality. If this interpretation is correct, then the quantum cosmos includes an infinite number of parallel universes, constantly branching with each quantum event. At every second, countless trillions of quantum events occur in every cubic centimeter of space, creating an unimaginable array of parallel realities. Somewhere in this multiverse, there's a version of you that made a different decision this morning. A version of Earth where the dinosaurs are not extinct. A version of space where the stars have come together in a completely different configuration. It sounds like science fiction, but it's a serious physical theory that is supported by many prominent physicists. And the most striking thing is that it cannot be refuted, because we will never be able to observe these parallel branches of reality. We are locked in our own quantum history of the universe. Let us now consider how quantum effects manifest themselves in exotic space objects. Take pulsars, rapidly rotating neutron stars that emit regular pulses of radiation. Some of them rotate hundreds of times per second, and their internal structure is controlled by quantum mechanics at the macroscopic level. Inside the pulsar, there are layers of matter in exotic quantum states. There may be superfluid neutron fluid that flows frictionlessly, and superconducting proton matter that conducts electricity with zero resistance. These quantum states, normally only observed in laboratories at temperatures close to absolute zero, exist at the heart of a pulsar at temperatures of millions of degrees, thanks to extreme pressures. Even stranger things can happen in the cores of the most massive neutron stars. At high enough pressure, neutrons can decay into their constituent quarks, forming quark matter, a state of matter that may have existed throughout the universe in the first microseconds after the Big Bang. This quark matter behaves like a quantum fluid, the properties of which we are only beginning to understand. There is even a hypothesis about quark stars, objects composed entirely of quark matter, denser than neutron stars, but not collapsing into black holes. If such objects exist, they are giant quantum droplets the size of a city, governed by the laws of quantum chromodynamics. Now let's talk about the event horizon of a black hole from a quantum perspective. According to classical theory, an event horizon is simply a mathematical boundary, a one-way mirror in space-time. But quantum mechanics paints a very different picture. The event horizon can be a place of intense quantum activity. There's an idea called the firewall paradox. She suggests that to an outside observer, the event horizon may not be empty space, but a wall of high-energy particles, a wall of fire created by the rupture of quantum entanglement between the particles falling into the black hole and the Hawking radiation escaping away. If you try to cross the event horizon, you can be instantly incinerated by this quantum firewall. But this contradicts Einstein's equivalence principle, which says that a free-falling observer should feel nothing special when crossing the horizon. This is one of the most poignant paradoxes in modern physics, indicating that we need a deeper theory that unifies quantum mechanics and gravity. Perhaps the solution lies in the holographic principle, the idea that all information about a three-dimensional volume of space can be encoded at its two-dimensional boundary. For a black hole, this means that all the information about what has fallen inside is stored on the surface of the event horizon in the form of a quantum hologram. From this point of view, a black hole is like the most powerful information storage system in the universe, where each square centimeter of the horizon stores the maximum possible number of quantum bits. This idea has profound implications for the entire cosmos. Some physicists have suggested that our entire universe may be a hologram, that the three-dimensional space we live in is actually a projection of quantum information recorded at the far cosmic boundary. Reality may be an illusion of depth created by quantum bits on the surface of space. Let's get back to the practical aspects of the quantum cosmos. Cosmic rays, the high-energy particles that permeate the cosmos, give us the ability to study quantum physics at energies unattainable in Earth's accelerators. When a cosmic ray proton collides with an atom in the Earth's upper atmosphere at close to the speed of light, it creates a shower of secondary particles, pions, kaons, muons, all of which obey quantum laws. The most energetic cosmic rays ever discovered carry energy equivalent to that of a tennis ball flying at high speed, but concentrated in a single subatomic particle. Where do these particles with such incredible energy come from? Perhaps from the active nuclei of galaxies, where supermassive black holes accelerate matter to relativistic speeds. Or from cosmic strings, hypothetical one-dimensional defects in the fabric of space-time left over from the Big Bang. Or even from the decay of dark matter particles. By studying these cosmic particles, we look into the most extreme quantum processes in the universe. They show us physics at energies, where quantum mechanics and relativity dance on the edge of their applicability, hinting at new laws of nature waiting to be discovered. Now imagine a quantum sensor aboard a space telescope using entangled photons to achieve measurement accuracy beyond the standard quantum limit. Such sensors could detect gravitational waves from pairs of black holes merging at the edge of the observable universe, or capture the faintest traces of exoplanet atmospheres by analyzing the spectra of their stars with unprecedented resolution. Quantum interferometry in space opens up the possibility of creating a virtual telescope the size of Earth's orbit or even the solar system. Multiple satellites, separated by millions of kilometers but connected by quantum entanglement, could work as a single giant instrument, resolving details the size of the event horizon of the black hole at the center of our galaxy, or even directly imaging the surfaces of exoplanets in other star systems. Quantum technology is also revolutionizing deep space navigation. Quantum clocks based on the superposition of atomic states are so accurate that they would be off by less than a second over the lifetime of the universe. With such a clock on board, the spacecraft could determine its position in space with centimeter precision, using pulsar signals as space beacons. Quantum gyroscopes and accelerometers that use the interference of the wave functions of atoms could detect the slightest changes in the ship's motion caused by the gravity of invisible objects, or even subtle distortions of space-time from passing gravitational waves. The spacecraft will become a sensitive quantum instrument tuned to the very fabric of space. There's an even more ambitious idea: to use the quantum effects of the vacuum itself for motion. The Casimir effect, where quantum fluctuations in the vacuum create a measurable force between closely spaced conductive plates, hints at the possibility of extracting energy from the quantum vacuum. While this doesn't violate the laws of thermodynamics, energy isn't created out of nothing, but redistributed from vacuum fluctuations. It could make it possible to create engines that run on the energy of space itself. Imagine a space sail covered with nanostructures optimized to maximize Casimir's force in a particular direction. Such a ship would literally surf on the quantum waves of the vacuum, slowly but steadily gaining speed without the need for fuel. Traveling to the stars could take millennia, but for a quantum space sail, it would be a perpetual wind at the back. Now let's turn to one of the most intriguing possibilities of the quantum cosmos: the quantum archaeology of the early universe. Each photon in the cosmic microwave background carries quantum information about the state of the cosmos 380,000 years after the Big Bang. But even more ancient information may be encoded in relic gravitational waves and possibly neutrinos from the first seconds of the universe. If we can detect and decode these primordial quantum signals, we will have a direct window into the moment when the entire universe was a quantum system. We could see imprints of quantum gravity, traces of extra dimensions of space, evidence of inflation, or even hints of what existed before the Big Bang. Some theories suggest that our universe was born from quantum tunneling from a previous state, perhaps from a collapsing universe that has achieved a quantum bounce, or from a quantum fluctuation in an ever-existing multiverse. Quantum archaeology can give us answers to these fundamental questions about the origin of all things. Let's also look at the role of quantum phenomena in life itself and its possible existence in the cosmos. Recent research suggests that quantum effects play an important role in biological processes. Photosynthesis in plants uses quantum coherence to transfer energy, with almost 100% efficiency. Birds can use the quantum entanglement in their eyes to navigate the Earth's magnetic field. Even our sense of smell can work on the principles of quantum tunneling of electrons. If life on Earth uses quantum effects, then alien life in other parts of the cosmos may have developed even more sophisticated quantum biological systems. Imagine an organism on a planet with high levels of radiation, using quantum entanglement to instantly communicate between cells to protect itself from damage. Or a form of life in deep space, existing at temperatures close to absolute zero, where quantum effects dominate thermal noise, allowing incredibly complex quantum calculations in biological structures. Some scientists even suggest that consciousness itself may be a quantum phenomenon. If so, then intelligence in the universe could exist in forms we can't even imagine. Quantum superpositions of thoughts, entangled minds stretching across cosmic distances, or the collective mind of civilization existing as a single quantum system. This brings us to the exciting idea of quantum communication with potential extraterrestrial civilizations. The traditional search for extraterrestrial intelligence, SETI, focuses on radio signals traveling at the speed of light. But an advanced civilization could use quantum entanglement to create instantaneous communication channels across the galaxy. We wouldn't be able to intercept such messages if we weren't part of a predetermined network of entangled particles. Perhaps the cosmos is already filled with the quantum communication networks of ancient civilizations, invisible to us because we don't know how to tap into this quantum web. We're like people living in a world filled with radio waves, but not having a radio receiver. There may be an ocean of quantum information around us, a galactic internet of civilizations, and we don't even know it exists. Moreover, given the many worlds interpretation of quantum mechanics, there may be ways of communicating between parallel branches of reality. Imagine a technology that allows you to send messages not only across space, but also between quantum worlds. You could connect with an alternate version of yourself in a parallel universe where history has taken a different path. A civilization that mastered such technology would have access to the collective knowledge and experience of an infinite number of its quantum counterparts. Now let's dive into the quantum nature of space-time itself. On the scale of the Planck length, an incredibly tiny distance of about 10 to the minus 35th power of a meter. The smooth fabric of space-time, described by relativity, is likely to disintegrate into bubbling quantum foam. On these scales, space and time become indefinite, shimmering, and fluctuating. In this quantum foam, tiny black holes, wormholes connecting distant points in space, and even bubbles of infant universes can spontaneously appear and disappear. Every point in the cosmos, when viewed at a sufficiently shallow resolution, is a raging ocean of quantum geometries, where the very concept of distance and duration loses its meaning. String theory, one of the leading candidates for the theory of quantum gravity, suggests that the fundamental constituents of reality are not point particles, but tiny vibrating strings of energy. Different modes of vibration of these strings create different particles that we observe: electrons, quarks, photons. Even gravity arises from the vibrations of strings. But for string theory to be mathematically coherent, it is required that the universe has not 3 spatial dimensions, as we perceive, but 10 or even 11. Where did the extra dimensions go? They're twisted, compactified to sizes so small that we do not notice them, perhaps just to the Planck scale. The shape of these hidden dimensions determines the laws of physics in our three-dimensional universe. It's as if the cosmos were a giant musical instrument, where the geometry of the extra dimensions dictates which notes, which particles and forces can exist. In other regions of the multiverse, the extra dimensions can be twisted in a different way, creating universes with completely different laws of physics. There's a surprising possibility that these extra dimensions may be larger than we think, but we are trapped in a three-dimensional membrane floating in a higher dimensional space called a beam. Gravity can seep into these extra dimensions, which would explain why it is so weak compared to other forces. Dark matter and dark energy may be manifestations of gravitational effects from higher dimensions that are directly invisible to us. Moreover, these extra dimensions may contain parallel branes, other three-dimensional universes floating near ours in higher space. When two branes collide, colossal energy is released, which could look like a Big Bang to observers on the brain. Our universe could be the result of such a collision, and new collisions could be happening in other parts of the beam right now, creating new universes. The quantum nature of gravity may also explain the strange coincidence between the entropy of a black hole and the area of its event horizon. Jacob Bekenstein and Stephen Hawking have shown that a black hole has an entropy proportional to the area of its horizon, rather than its volume, as one might expect. This hints that information about the contents of a black hole is stored on its surface in the form of quantum bits. If you divide the event horizon into Planck pads, squares with a side of the Planck length, the number of these pads is exactly equal to the maximum number of quantum bits of information that a black hole can hold. Each Planck site stores 1 bit. It's a deep connection between quantum information, gravity, and the geometry of space. The holographic principle generalizes this idea to the entire universe. It assumes that all information about three-dimensional space can be encoded on its two-dimensional boundary. For our universe, this means that everything that happens inside the cosmic horizon, the boundary of the observable universe, can be described by quantum information on this distant surface. From this point of view, we live inside a cosmic hologram. The three-dimensional reality we perceive is a projection of two-dimensional quantum information. The depth of space may be an illusion created by the entanglement of quantum bits at the cosmic boundary. This radically changes our understanding of what is real and what it means to exist in space. Let us now consider the quantum aspects of cosmological inflation, a period of exponentially rapid expansion in the first fractions of a second after the Big Bang. Inflation was caused by a quantum field called an inflaton stuck in an excited state. As this field slowly rolled down to its minimum of energy, its vacuum energy led to an exponential expansion of space. But the inflaton field was quantum, subject to quantum fluctuations. At different points in space, it fluctuated up and down randomly. In areas where the field randomly fluctuated upwards, inflation lasted longer, creating more space. In areas where it fluctuated downwards, inflation ended earlier and matter began to form. This means that inflation has created not a single universe, but an infinite number of pocket universes, each in its own bubble of space-time. This is eternal inflation, a process that, once started, never ends globally. Somewhere in the multiverse, inflation is still going on, giving birth to more and more pocket universes from quantum foam. Our observable universe is just one tiny bubble in an endless ocean of bubble universes, each with its own history, perhaps its own laws of physics. Quantum fluctuations during inflation have determined which universe we will find ourselves in. In a sense, quantum randomness has chosen reality for us. What's more, the same quantum fluctuations of the inflaton created tiny inhomogeneities in the energy density of the early universe. These inhomogeneities, stretched by inflation to cosmic proportions, became the seeds for the formation of galaxies. Every galaxy in the sky started as a quantum fluctuation, a random quantum noise in the primordial field. The cosmic microwave background preserves the fingerprint of these primordial quantum fluctuations in the form of tiny temperature variations. When we look at a map of the microwave background, we literally see quantum mechanics written on the sky. We see an image of the quantum state of the universe at a time when it was smaller than an atom, enlarged to cosmological scales. Another surprising consequence of quantum cosmology is related to the problem of the arrow of time. Why does time flow in one direction, from the past to the future? Why do we remember the past, but not the future? The fundamental laws of physics, including quantum mechanics, are time-symmetric. They work equally well in both directions. The answer has to do with entropy and quantum entanglement. The universe began in a state of very low entropy, a highly ordered quantum state at the moment of the Big Bang. Since then, entropy has been constantly increasing, and this increase in entropy creates an arrow of time. But entropy is closely related to entanglement. As the universe evolves, systems become more entangled with each other, and this increasing entanglement creates the direction of time. In a sense, the past is a direction toward less entanglement, and the future is toward more. Every quantum interaction in the cosmos increases the overall entanglement of the universe, and the cumulative effect of countless quantum events creates an irreversible flow of time. Some physicists suggest that in the distant future, when the universe reaches a state of maximum entropy, the so-called heat death, time will cease to exist in some sense. The universe will be in a state of maximum quantum entanglement, where all possible correlations have already been established, and there is nothing left to change. This will be an eternal quantum equilibrium, where the concept of before and after loses its meaning. But even in such a dead universe, quantum fluctuations will continue to occur at unimaginably long intervals, much longer than the current age of the universe to the extent of its age. The rarest quantum fluctuations can spontaneously create new regions of reduced entropy. Random structures can form, even new universes in miniature within a lifeless cosmos. There's even the Boltzmann brain hypothesis, the idea that in such a dead universe, quantum fluctuations could randomly assemble a functioning brain full of false memories, existing only for a moment before decaying. If the universe exists forever, there will be an infinite number of such random brains. Statistically, we are more likely to be Boltzmann brains than real beings who evolved in an ordered universe. This paradox points to deep problems in our understanding of cosmology and quantum mechanics. Perhaps an eternal universe is impossible, or the laws of physics change in ways that prevent infinite existence. Or our universe is just a temporary fluctuation in an eternal multiversum that will eventually dissolve back into quantum foam. Let us now discuss practical experiments that explore the quantum nature of the cosmos. Gravitational wave detectors, such as LIGO and the future space-based LISA, are some of the most sensitive quantum instruments ever created. They measure the stretching of space caused by passing gravitational waves with an accuracy smaller than the size of a proton at a distance of a few kilometers. At these levels of sensitivity, quantum noise becomes a serious problem. The photons of the laser beams in the detector obey quantum statistics, creating random fluctuations in the measurements. Engineers use compressed light, a quantum state where uncertainty is redistributed between different properties of light, to reduce noise and increase sensitivity. Future gravitational wave detectors could use quantum entanglement between photons or even between massive mirrors to achieve even greater sensitivity. They could detect gravitational waves from the Big Bang, carrying information about the quantum nature of space-time in the first moments of the universe. There are also experiments trying to detect quantum effects in gravity directly. One approach is to use a quantum superposition of massive objects and see how gravity affects their wave functions. If you can place a massive enough object, perhaps a tiny golden sphere, in a quantum superposition of the two positions, you can observe how its own gravitational field interacts with the superposition. Such experiments are incredibly difficult because any interaction with the environment destroys quantum superposition, a process called decoherence. But if they are successful, they will prove that gravity obeys quantum laws and help us understand how to unify quantum mechanics with general relativity. Space provides a natural laboratory for the study of quantum physics in conditions that are impossible on Earth. In deep space. In conditions of near absolute vacuum and extremely low temperatures, quantum phenomena manifest themselves with crystal clarity unattainable in terrestrial laboratories. Interstellar space is the most advanced quantum laboratory created by nature itself, where particles can maintain quantum coherence for light years without undergoing decoherence from interaction with the environment. When we look at the starry sky, we see not just a beautiful picture of distant suns. We see the quantum universe in action. Every photon that reaches our eyes has gone through a quantum journey, existing in a superposition of all possible paths at once, until it reaches your retina and collapses into a specific state. At that moment, you become part of the quantum history of the cosmos, an observer whose measurement changes reality. We live in an age where the line between quantum physics and cosmology is blurring. The smallest and the largest are connected by inseparable threads. Quantum fluctuations gave rise to galaxies. Entanglement connects opposite edges of the universe. Black holes store quantum information. Space-time itself may be a quantum phenomenon. In the coming decades, we will build quantum communication networks that stretch across the solar system. We will send quantum sensors to distant worlds, capable of detecting signs of life through the finest quantum signatures. We will look even deeper into the past of the universe by reading the quantum information recorded in the cosmic microwave background and primordial gravitational waves. Perhaps we will even learn to manipulate the quantum structure of space-time, opening pathways to stars that seem like science fiction today. Quantum teleportation, which today works at a distance of kilometers, tomorrow can connect planets and star systems. Quantum computers on a cosmic scale will be able to simulate entire universes, helping us understand our place in the multiverse. But there is a deeper truth behind all these technological marvels. The quantum cosmos teaches us humility and wonder. It shows that reality is much stranger and more beautiful than we could have imagined. That at a fundamental level, the universe is not a clock-like mechanism, but a quantum dance of possibilities where every observation, every dimension participates in the creation of reality. You who are sitting here listening to these words are made up of atoms born in the depths of the stars billions of years ago. The electrons in your neurons obey the same quantum laws as the electrons at the edge of the observable universe. You are part of the quantum fabric of the cosmos, a consciousness that has emerged from quantum processes capable of reflecting on its own quantum nature. Quantum space is not just a topic of scientific research. It's a new way of seeing reality, where everything is connected to everything, where the observer and the observed are inseparable, where the past, the present, and perhaps the future are intertwined through quantum entanglement. It is a cosmos full of infinite possibilities, where every quantum fluctuation can give rise to new worlds, new realities, new forms of existence. We are on the verge of great discoveries. The next generation of quantum space missions may find signs of quantum civilizations using technologies we only dream of. We can find evidence that we live in a multiverse, or discover entirely new laws of physics that govern quantum gravity. We may even once answer the most fundamental question of all: why there is something and not nothing, and why quantum laws are the way they are. The quantum cosmos is infinite in its complexity and beauty. Each answer gives rise to dozens of new questions. Each discovery opens the door to even deeper mysteries. And this is its greatness, in the fact that the universe will always surprise us. There will always be something new to explore, something unknown on the horizon. Thank you for coming with me on this incredible journey through quantum space. Remember that every time you look up at the night sky, you're looking at a quantum symphony unfolding on a cosmic scale. You see photons that have traveled for millions of years in quantum superposition, only to collapse in your perception. You are part of this cosmic quantum dance, an observer and a participant at the same time. Keep looking up, keep asking questions, keep wondering. The quantum cosmos awaits, full of endless wonders, ready to open up to those who dare to peer beyond the veil of everyday reality into the quantum abyss from which everything is born and to which everything returns. It was the Quasarea Channel. See you again in the vastness of the quantum cosmos, friends. Remember, reality is quantum, the possibilities are infinite, and the universe is much stranger than we can imagine. Keep exploring, keep dreaming, and maybe one day we'll uncover the ultimate mysteries of the quantum cosmos together.